I see you come Friday. The flavor of the quiz will be part 1. Identify the functional group. The question types. Part 2. I will give you a molecule. You'll be asked the functional group again, as well as to name it. Part 3. I will give you a name and you will draw it. Or I will give you a functional group and you will draw it. Yes. There's nothing surprising on there. There is not a single IB question on there. It is meant to be short, fast, and do you know what a ketone is? What? I will give you so in one part I will give you a molecule and ask you what its name is. So I will draw butanone and ask you to name it as butanone. I don't want to lie to you, but I also don't want to tell you the question. How do I do this? Fine, the question is, hey Karthika, draw me a molecule with an amine. So you're going to have to not draw a functional group, but a full molecule. I don't think we really know how the R thing works very well. And so to make sure that you have hydrogens everywhere they belong, I expect it to be like a molecule. But your molecule can be different than Elizabeth's. I just want to see the functional group. So if you looked all through that, it was wrong every time. Did you feel that? No one screamed at me. Those are all classes, but they called them functional groups. The IB is the only place I've ever seen those words like flip-flops. So you do need to, we need to get good at that. I will not count you wrong. I will just circle it and write the other word. Yes.
What would you write?
So I would say, hey Karthika, draw me a ketone. But if I drew you a ketone, I would say, hey Karthika, what's the functional group? Or what class is it in? Those would both be legal. Right? So speaking of functional groups, okay. Speaking of functional groups, let's talk about alcohols. Oh, Leo strikes again. Can you guys picture some alcohols? In your head.
Oh, yeah.
So what I'd like you to consider is the molecule butan-1-ol. That would be the molecule C4H9OH. And I'd like you to write down some structural isomers of butan-1-ol that are alcohols. So I know that there are probably some ethers that you can draw, but I don't want any ethers. I only want molecules that are alcohols. And so I've tried to force that by putting this OH here. So that's my hint. So I know that this isn't specifically butan-1-ol, but that would be an example. So I'm wondering how many discrete different molecules you can draw that have the formula C4H9OH or are isomers in the same class. Terrible, those hydrogens, terrible. Are there any other alcohols that we can draw? Or given that there are 2 other alcohols, what are they? So we are looking for all of the alcohols that have the formula C4H9OH. I said 1-butanol. Back table said 2-butanol. Yes, they did. I heard them.
No, you didn't.
I know. Audrey's saying no, like she doesn't know. What? butanol would not have the same structural formula. To close that cycle, you would have to give up 2 hydrogens.
Isn't that all you do?
So that's all we can do with the chain of 4, which I think is your problem, folk. But what if we didn't have a chain of 4? A chain of 5?
If you did a chain of propane, like, and then you have one, like, either 1 or 2, and then the OH is taking off the other.
That's what I heard, Rami. I hope that's what you
Yeah,
said.
that's what I meant.
Okay, so this is one of them. And this would be methyl 1-propanol.
For the mental one, you have to place what seed.
What?
For the, you don't have to say which seed the mental is on.
The methyl can only be on carbon 2, so you don't have to say it. I was just gonna ask you that question, why I didn't write the 2. So you could ask me that question. It's optional. It's the only place you can put the methyl. So if you put the methyl on 1, it would be a bute. If you put the methyl on 3, it would be a bute. So the only place a methyl can go is on 2. And so we like to be proud of ourselves and not write the 2. Like, haha, we see that this is the only one. Let's not write it. Okay, so Rami gave me that. She said what we can do instead of having a chain of 4 is we can branch that chain and make a methyl propane. She put that, I think that's where she put the OH. And Emma's saying that we could put that OH somewhere else. We could put the OH right here, not in the 1 position, but instead in the 2 position. And so this molecule would be methylpropan-2-ol, or 2-methylpropan-2-ol, or 2-methyl-2-propanol. So many choices. I'm gonna be consistent, because I misread that. We all misread that. Yes?
What's the number for labeling of the alcohol between the?
It's a choice. So old school puts the number in front, the modern approach to put it in the middle. Because I put it in front of this one, I said I was gonna put it in front of this one. But I feel like Amarachi probably said propan-2-ol because she's probably cooler than I am. IB will count you correct wherever you put the number of the ol. So if you write 1-propanol or propan-1-ol, if you write 2-propanol or propan-2-ol, you get the mark. I don't know if that's gonna be true for my sophomores, but for y'all it's true. So what I'd like to do is I'd like to think of a way that we can classify these alcohols a little bit further. And the way I'm gonna do that is I'm actually going to look at the carbon that is attached to the oxygen, and I'm gonna count the number of carbons that are attached to it. So this is the carbon that's attached to the oxygen. How many carbons are attached to it? Okay, so you guys are saying 3 because you count very well, but what I mean is directly bonded to it. So this carbon has 2 hydrogens and 1 carbon. Like, it wasn't a good question, I knew that. And so the answer to my question is that this has a singular carbon attached. And so I'm gonna refer to this as a primary alcohol.
So not the primary, secondary, it's not like,
So it means kind of different things for the amines.
okay.
For the amines, it is, if you're looking at the nitrogen, how many carbons is it attached to?
Yeah.
Here, it means if you're looking at the OH, you find its carbon and how many carbons that one is attached to. So here we're not looking at the oxygen, it's always attached to 1 carbon. We're looking at the oxygen's carbon and counting. So how do you think you would call its neighbor, the butan-2-ol?
Secondary.
Secondary. Again, if this is the carbon in question, it has 2 carbons attached, we call him secondary. How about this guy? If we look at this carbon, how many carbons is it attached to?
1.
So it's primary. And the last one,
Tertiary.
Is it possible to have a quaternary alcohol?
No.
Why not?
Because then the fourth one would have to replace the OH, and that wouldn't be.
Carbon can only have 4 bonds if one of them's to an OH. I can't have 4 more carbons on there. So they're primary, secondary, and tertiary alcohols.
Can you explain why that one's a tertiary alcohol?
So I'm looking at the carbon that's attached to the OH, and I'm just counting the number of carbons attached to it directly.
Oh.
The number of carbon-carbon bonds that carbon has. So there are primary, secondary, and tertiary alcohols. So I'd like to go back in time. Back to a happier place. You called it chapter 5.
What's chapter 5?
Chapter 5, energetics or thermochemistry, is that what I prefer to call it.
Was it happy, really?
January, remember how you had no worries in January? You didn't even have an extended essay topic in January, I bet.
I always have worries in chemistry.
We definitely
You
did.
did in January?
It was due
Oh, you got it in
before-
October.
It was due before,
You're right. Okay, what did you have in January? You didn't have,
I still don't have.
did you weep?
What?
Never mind.
Yesterday when you left, did you just like cry, full cry?
No, I went to, Good Eye, I searched it up, and started searching.
Did you find Carl, the tutor? Carl has really bad IA topics. Don't use Carl's website.
If you, like, if you go on Google, right?
Yeah.
And you know how whenever links are like clicked, it's purple?
Yeah.
If you search up IA topics in chemistry, I think like the first 2 pages are just all purple. It's all purple.
I feel it. I just don't recommend Carl,
That's me
everyone.
for bio.
I'll recognize him. I recognize his work. He's into superfoods.
Oh, the way.
Oh, and you're on Team Nigeria and superfoods.
Tag.
Naomi, Tenny, Kowo.
Oh!
I ain't playing, like, this is,
Is that it?
and I think they all took it from
Shayun.
Shayun, maybe.
She said they pass it down to each other.
Just pass it down.
Yes.
Because you like Should we continue the magazine?
I don't know, I'm looking forward to finding out.
Don't worry.
Okay, so can you write down a combustion reaction?
Probably something plus alcohol, water comes out, and oxygen equals CO2 plus H2O. Yeah. It's alcohol. Wait, it should be different like
Count away, my friendly.
Add oxygen to alcohol to make water.
Yes, if you burn alcohol, you make water.
I feel good about it.
In chapter 5, section 3, you learned that we could look at the bonds that were broken and the bonds that were formed. And we could combine the amount of energy that was required to try to determine the overall change in enthalpy of this reaction. So the delta H of any chemical reaction could be written as bonds broken minus bonds formed. And looking at these beautiful molecules that you helped me draw, I'm curious if you can make any comments about the amount of energy I would get out for 1-butanol, 2-butanol, methyl 1-propanol, and methyl 2-propanol.
She said negative.
It's okay. No negative, it's combustion.
What is
Increasingly more negative. I know it's decreasingly or decreasing.
So, like, let's look. What bonds would have to be broken here? I have 1, 2, 3, 4, 5, 6, 7, 8, 9 CH bonds. I have 1, 2, 3 CC bonds. I have 1 CO bond. And I have 1 OH bond. How would that compare for the one that's maybe most different, the tertiary alcohol?
3, 6, 9, 1, and 2. Same CH, but it doesn't have the OH bond.
No, it's right there.
No matter structure, so some things should be different when they break. What assumption have I made in using 5.3?
It's an average. It's average mental. So is that the representative?
Okay, so they are averaged across representative compounds, that's great. So we're pretending that all carbon-carbon bonds are the same, all oxygen-hydrogen bonds are the same. What else are we assuming when we use 5.3?
No heat is lost during gaseous state.
Is it gas? The gaseous state?
We're assuming that everything is a gas. And all of these alcohols, do you know what phase they are? They're liquids. Why would they be liquids?
Considering the gas.
Is the length of the carbon chain.
But even methanol with a length of 1 is a liquid.
Just cause.
What causes something to be a liquid at room temperature?
That's a good question.
We're now in chapter 4, part.
That was even worse. Hydrogen bond. I got something right.
So Audrey's saying that all of these molecules can hydrogen bond, so the strong intermolecular attractions between these molecules mean at room temperature, there's not enough energy to separate them. So you guys are saying that you don't expect all of these answers should be the same because in real life they're 4 different things. And so Audrey might go on to say that she thinks that this molecule would have the strongest intermolecular forces and so perhaps the most energy released when you burn it. And this one, which looks like a bit of a sphere, would have the weakest intermolecular forces and so the most different value from the long skinny. I love it. That was just like a...
The longer one would have
The long skinny one, the noodle shaped one, is harder to separate than the round shaped one. I try to talk about using chopsticks, but you guys seem to have just really different ideas of what I can pick up with a chopstick than I do. So I've like moved away from that.
Was it rice
why
and
is that
noodles?
the case?
Huh?
Why is that long?
Because it has the highest surface area. So if you
okay.
think about surface area, the thing with the smallest surface area is a sphere.
Yeah.
And this molecule is more close to a sphere with this central carbon with 4 like similarly sized things around it than that one with that long chain of 5 things in a row.
Surface area.
So the surface area here is small, and so the ability of us to interact is smaller, so the London dispersion forces would be weaker.
Is that
Van der Waals, I'll take it. Van der Waals includes both London dispersion and dipole-dipole.
so is that like the surface area thing?
They are proportional to the surface area. Uh-huh. This is a true statement? Okay. Yeah, Luke's not here, I don't know why. Chloe and Melania moved to the other section.
In a minute, it's down.
Men and STEM. Quinn is in Trinidad.
They all migrated.
We've only lost one. There's supposed to be 2 sections of 15, but one of them wasn't in HL last year, so they're not in HL this year. See how easy that math was? If you had to compare combusting an alcohol to combusting an alkane, which one do you think would produce more energy? Audrey told me this would be a negative number. I'm balancing. Y'all discuss among yourselves. I tried to balance them similarly. I know not everyone loves my fractional coefficients, but I'm totally at peace with them, so you know, sucks to suck.
Do we have to keep that coefficient of 1 anytime?
So, I mean, I feel like to compare it to this, having 1 for both would be great. If I'm using, I forgot the table number because it's been a hot minute since we've been here. If you're using table 13, the implied coefficient is 1.
Oh, so the rule, because I remember there was a rule where you
Yes.
have to keep that.
Coefficient is 1 if you're using table 13. So if I were to look up these values in table 13, which I'll do just for you, Maha.
Right, what is that?
Would it be,
What? 30 double
those numbers are in kilojoules per mole. They're straight from table 13 because, you know, going down memory lane. I get less energy out of the alcohol.
Can you explain why? Trade oxygen.
It's because there's already an oxygen in here. What is the process of oxidation doing? Adding oxygen to the carbons. What does this alcohol already have? It's already somewhat oxidized. This molecule has already gone down the path a little bit. If you think about energy cycles, 15-point dose, you could imagine that you could add one oxygen here to make this C4H9OH, and then add the rest of the oxygens. I'm not going to try to count. So you don't. I've already partially oxidized it to get to the alcohol. I've already given up some of the energy that I could get out of my burning. Moab is bueno, it's not bueno. That's good. An alkane will give you more energy than an alcohol. That will always be true. The reason is because alcohols are already partially oxidized. They already have that oxygen inside. So can you oxidize an alcohol? Yeah, you can burn it. Fair? When you burn things, do you only get CO2 and water? This is the definition of complete combustion. This is if everything goes perfectly. We might also get carbon soot. We might get carbon monoxide. It is a very vulgar process that just breaks this molecule apart into tiny little pieces and spits out global warming. I don't know. We are now in organic chemistry, and I would like to teach you something new and wonderful.
Literally just knew.
Yep.
Alkanes, when it's moving it and it would be less negative
Alkanes are more negative. They release more energy.
and more negative.
More negative. This number was 26. The other number was 28. Both negative. We classified alcohols as primary, secondary, and tertiary. And instead of lighting this stuff on fire, what I'm going to do is I'm going to add an oxidizing agent. And the oxidizing agents that I'm going to use are potassium permanganate and potassium dichromate. So instead of using oxygen as the oxidizing agent, as the thing that is adding oxygen, I'm going to use a chemical. And when you use that chemical, you need to use it in the presence of acid. So I will say the words, quote, quote, acidified potassium dichromate. We will refer to this as the reagent in our very first organic reaction. It's not the reactant per se. The reactant is going to be an alcohol. The reagent is sort of what it is reacting with to turn it into something new and marvelous and organic. The reason that there are two is because one is a little bit stronger. One is a little bit weaker, a little bit more subtle. I will always use acidified potassium dichromate if I am given the choice. Every time, that is the one I will pick. If someone says, write down the reaction for the oxidation of some alcohol, I choose the acidified potassium dichromate because it's going to give me slightly more options. But if a test question says they're using permanganate, so be it. Who cares? Do you notice that both of those materials are transition metals? So they're in row number 4 in the middle of the table.
Why does it need to be those specific compounds? Can you not just use
because these two things are in such positive oxidation state. So if you remember a little bit about charge, you might recall that potassium is +1, that oxygen is -2. I have a +1, I have 4 -2, that adds up to -7. Overall, this compound is neutral, so manganese here has an effective charge of +7, or 7+, or 7 in Roman numerals. Like, I'm not too worried here, I'll do good work. I'll do good work. Oxidation number.
What is the slash hydrogen?
You must do this in an acidic environment. If you don't do it in acid, you won't get the results that I want. We're gonna talk more about this in chapter 9, because chapter 9 is specifically about oxidation and reduction. So today I'm more interested in what the products are gonna be.
What chapter are we in right now?
10. If I play the same game here for chromium, 7 times -2 is -14, 2 times +1 is +2, -14 and 2 is 12, negative. So the chromiums must add up to a +12, or the chromiums must be in a positive oxidation number of 6. Both of these things are very, very hungry for electrons. Both of these things are likely to be reduced. How are they going to be reduced? They're going to find an alcohol and suck its electrons away. They're going to oxidize it. So that is why I choose those materials. Aditi might think I could use some like technetium, but like I don't got none. Molybdenum, it's quite expensive. So it's like they're reasonable in a high school lab and they have really big positive oxidation numbers. No, there are 2 choices that you can use. So there are 2 possible reagents for the oxidation of an alcohol. No, we haven't talked about how this is gonna matter. It's clearly gonna matter because we started there. So again, we took alcohols, we broke them down into 3 classes. I introduced 2 oxidizing agents. Oxygen is an oxidizing agent. It makes like waste products. These 2 oxidizing agents are gonna allow me to make organic compounds. So I'm gonna show you what the products would be. You take a primary alcohol, like 1-butanol, in the presence of acidified potassium dichromate. There are actually 2 things that you can form. I'm going to draw you 2 of those. It ends up that this reaction is quite slow, and so what we're going to do is we're going to heat it up. And in one case, I'm going to describe the heating process as, it doesn't need quotes, I don't know why I'm in a quote mood, distill. And in the other case, I'm going to describe that heating process as reflux. Those 2 words are in blue and written out because I don't think that Sophia knows yet what reflux is. Is that fair?
Very fair.
Okay, like she may be an A&P and have an idea what reflux is in that context.
Yeah.
And we'll see if it's the same thing, but like I'm writing them down because I don't think you know them. If you take a primary alcohol, butanol is a singular example of that, in the presence of an oxidizing agent, and you heat it using distillation, you will make an aldehyde. The aldehyde is going to be formed by taking away this hydrogen, and making a double bond to that O. We do not have a mechanism for this. I cannot show you how the electrons are moving around or why those H's magically go away. But what is important, and the reason that I defaced my structure over here, is because I want you to know, believe, recognize that the location of the alcohol is the same as the location of the aldehyde. The O did not move. That's what I need you to see. The O did not move. So I'm going to turn this back into the alcohol it was. And I'm going to come over here and I'm going to show you the CHO it can become butanol. If you distill, you will make butanol. If you reflux, you will first make butanol, But in fact, the reflux process is a little bit more hardy. Like it's a harder reaction condition. It will do a little bit more oxidation. And in fact, you will continue to oxidize this product and you will make another O right there. You will add yet another oxygen to this and you will make a carboxylic acid. Again, there is no mechanism. I cannot show you step by step how that occurs, but I can show you that the product is going to have now 2 oxygens at the same carbon that the alcohol was originally at. So that's what's important to me. If I have that terminal oxygen, a primary oxygen, and I oxidize it, it is possible for me to get an aldehyde or a carboxylic acid. This is a gentle approach, and this is the not gentle approach, the firm approach.
So sometimes like with like Revlon, they require us to like have like a cap on and we don't ever take it out for too long because it's sour. So but like there's no oxidation option in the process.
Yes, there is. There's oxygen.
There's oxygen.
Absolutely. So if you wanted to make vinegar, and if you know the character for vinegar, I'm even more proud of you if you can throw that one down. Can you draw vinegar in Mandarin? Vinegar is the acid that wine turns into. It is the alcohol in wine that continues to be oxidized to make vinegar. So I had a French student once upon a time, and they were, like, unsurprisingly, as I reflect upon it, making vinegar on their counter. Oh yes, we make home vinegar out of wine. They would just take any wine that wasn't consumed and appropriately make it into vinegar.
Distilled white vinegar. That's right.
So what's the exact difference between adding an oxidization agent to a distill versus reflux?
We're getting there. Again, that's why I have the blue, because I don't think you know those words.
So why do we need that oxidizing agent if like we have oxygen? Is it like faster that way?
Yeah, it's faster and it's specific. Like I could do this in a lab setup without accidentally burning it and making CO2. Oxygen is a really tough oxidizing agent, so it might make some other products. And yeah, vinegar takes time. I don't have time. So I told you potassium permanganate was like a little bit tougher than potassium dichromate. And the reasoning for that is you can only do this process with permanganate. It is not possible to catch the aldehyde. The oxidation happens fast enough that we can't get the aldehyde, we go straight to the carboxylic acid. In distillation, something like that. I have the glassware, so maybe I'll be nice enough to set it up for next time. I did not write this down. It's something I had to tell you today. I thought we'd be somewhere else by now. What happens is you take the mixture. So the mixture is going to be alcohol and acidified potassium dichromate. And you're going to allow it to react. As it reacts, it takes that alcohol and first converts it into an aldehyde. What is the difference in intermolecular force between the alcohol and the aldehyde? I don't break any bonds when I try to boil something. intermolecular forces, alcohols, aldehydes.
Oh, wait.
Waiting. Audrey's gonna say what she said earlier. What is the difference between the intermolecular forces in aldehydes and alcohols? So, I'm hearing that this has hydrogen bonds and that this does not have hydrogen bonds. So what I'm gonna do is I'm gonna take this to a temperature, that's a really sad looking thermometer. And that temperature is gonna be such that the alcohol will not boil, but the more volatile aldehyde will. And when that aldehyde boils, it's gonna go into the gas phase, and it's gonna go down this tube. This tube is known as a condenser, and it's actually a jacketed tube. I flow cold water in one side, and the cold water is going to interact with that aldehyde in the gas state, and it's going to condense until it flows directly over here into this really pretty round bottom flask. I'm going to capture the aldehyde. So that is the process of distillation. If Karthika took the wine that was left over on Audrey's counter and instead of trying to make vinegar of it, decided she wanted to make brandy, she would have wine over here. She would heat it to a temperature where alcohol boiled, but water did not. And the alcohol would slowly but surely condense over here. So if you talk about distilled spirits, alcohol has a lower boiling point than water, so you can separate alcohol plus water into water and alcohol.
So distillation is the process of like turning an alcohol to an aldehyde?
Distillation is the process of separating two liquids by virtue of their boiling point. Distillation works for taking an alcohol into an aldehyde because the alcohol and the aldehyde have different boiling points. The aldehyde cannot hydrogen bond. It has weak intermolecular forces, a low boiling point, and because of that difference, I'm able to separate it. If I left the aldehyde over here in the presence of this oxidizing agent, it would continue to react and I would make the vinegar. The way we do that is a process known as reflux. I take the same round bottom flask, I take the same condenser, but I just reorient them. Take the same heating source, the only thing I can pretend to draw is a candle, I'm really sorry. You don't use a Bunsen burner because this stuff is flammable, it's really dangerous. You use something called a heating mantle, it's like a pillow that gets hot. It's like the blanket you put on your bed, but it like perfectly fits up against the round bottom flask. Yes, we have one. We need one, we have one. So here what we do is we take the same alcohol and acidified potassium dichromate. And what happens first is we make the aldehyde. When we make the aldehyde, what happens to it? It vaporizes. It has a low melting point and boiling point. But when it vaporizes in this condenser, it's going to turn back into a liquid, and gravity is going to pull it back down into the pot. So that's the reflux that Sophia's thinking about from A and P. You have acid in your stomach, it's going up your esophagus, you swallow it down. It's going up your esophagus, you swallow it down. The low boiling point things are going up this pipe, but when they get to the condenser, they condense back to the liquid and fall back down. So we force the aldehyde to stay in contact with the alcohol, and here we manage to make the carboxylic acid. The reaction will not continue beyond that. So we can take a primary alcohol and we can turn it into an aldehyde or a carboxylic acid. Now remember what we did to turn this into an aldehyde is we had to take away that H, we had to take away that H, and we had to make a double bond. Okay. I'm gonna draw you a secondary alcohol. Your secondary alcohol from earlier today was butanol. So if we had butanol, in the first step of this oxidation, what I just showed you is we removed two hydrogens. We removed the hydrogen that's directly bonded to the carbon, bye-bye. We remove the hydrogen that's directly bonded to the oxygen, bye-bye, and we build in a double bond. What kind of molecule is that? What is the class? That is a ketone. Secondary alcohols become ketones. Primary alcohols, because they have the O on the end, have to turn into terminal aldehydes and carboxylic acids. Secondary alcohols, because they have the O in the middle, have to turn into interior carbonyls, which we call ketones. In the second step, when we took an aldehyde and turned it into a carboxylic acid, what did we have to do? We had to remove an H and add an OH. We had to remove the H from the aldehyde, from the CHO, and add an OH. So let's see if we can go further with the ketone. Does this carbon have a hydrogen on it that I can remove? No. It will not turn into an ester. This is the end. Primary alcohols, aldehyde, carboxylic acid. Secondary alcohols, ketones, dead end. Now think about your tertiary alcohol. Your tertiary alcohol was this one. Can I remove a hydrogen from this carbon to make the carbonyl? I don't have one. Tertiary alcohols do not react. So the way I'm going to draw this from now on, so I'm going to have a very large map. I'm going to draw a surprisingly large number of times. And in that map, I'm going to list the class names because I'm better at them. And I'm going to show you that an alcohol can be primary, secondary, or tertiary. And in the presence of acidified potassium dichromate, and heat, we'll see how artistic I get. A tertiary alcohol does nothing. I will signify that with the phrase NR, which means no reaction. A secondary alcohol will turn into a ketone. And a primary alcohol under distillation will become an aldehyde. Under reflux will become a carboxylic acid. And if you want to, you can keep reacting that aldehyde and throw this in. So I will have a map that shows the different classes of compounds that we spent the last couple days learning about, and shows you ways that we can change one into another. So this class doesn't become about naming really complicated compounds. Instead, it comes up with schemes to convert one thing into another. And so over here, we're going to have alkanes. And the question is, how do we do that? And so we'll fill in those blanks, over the next two classes. Marachi.
So how would you define reflux then? Is it the opposite of distillation?
So reflux is just heating such that nothing can escape. So distillation is removing that low boiling point product, and refluxing is just heating. So if you imagine yourself in a porphyrin lab at Rice University, where the first experiment you need to do as a chemistry major is, make porphyrin. That's the molecule that's like around chlorophyll or around hemoglobin. picture those things, the 4 nitrogens coming into the magnesium and chlorophyll, or the iron and hemoglobin. Y'all can't draw heme?
We never have it.
Well, that thing. Like porphyria is, yeah, you can do this also. So this is just heat. There's no choice here. You can't make the aldehyde with this. There are 4 heme groups and a single heme group. That is true. Okay, so if you're picturing yourself making that porphyrin product, picturing that it's important to you, so you've got to heat up something that's organic. Are you going to heat it in a sealed vessel?
If you want to do reflux?
I'm just saying in general, you have something and the procedure says add heat. Like right here, this says if I put in some acidified potassium permanganate and heat, I'm good to go. And so I'm envisioning I can't use some isopropanol, so we're going this way, but whatever. And I'm like, hey, Amarashi, put some heat in there, put some permanganate in there, and we're gonna end up with acetone. We're gonna make our own nail polish remover. Look at us go. We're gonna be rich. Homemade nail polish remover. The question is, are you gonna close the isopropyl alcohol? Because I know and you know it's super volatile, it smells. And especially if I was trying to heat it with a flame, I've erased my flame, but I still picture it there. Like having that open, like, ooh boy, that's gonna be really exciting. So I'm thinking I should just close it so it can't, Okay, I've talked her into closing it. Does anyone see a problem with closing it? It can explode, right? We're gonna make gas, we have made a bomb. And so to avoid making the bomb, but to experience the fact that, holy moly, these things are volatile, someone real smart came up with the idea of this jacketed condenser tube. I leave it open at the top, so I'm not making a bomb, but I'm also hoping that I can trick anything that goes into the vapor phase to trickling back down into my reaction container. So I'm hoping not to lose any material, but reflux is just like a fancy way of heating something so that you don't bomb. So my very first day of working at Rice in said majors class, I was going around setting these up with kids, and my TA, a lovely young first-year graduate student, put a glass stopper on top of everyone. And so then I was like, oh shit! So we ran around removing those. So I'm like sensitive to this bomb making thing. I'm very scared of making a bomb. That's
Can
not
we
my
make
goal.
acetone in class? That'd be cool.
What?
Can we make acetone in class?
There's your eye. There goes your eye.
Yeah.
I will try to have this set up.
Okay.
I'm not sure it'll be acetone. I don't know why you would care. I mean, you could smell acetone, I guess, and know that you made the right thing. You probably know what it smells like.
I just don't want to pay for it anymore. Yeah.
So you really want that? I got you.
We're just blowing up these.
It's just a fancy way of adding heat.
And then distill is removing up front, right?
So distillation also requires heat, but what's clever about it is that we're able to remove that lower boiling point material. Was this manageable? First reaction, oxidation?
There's, so there's more.
Sweetheart, yeah, that's the whole game.
Just make sure I get like the reflex part right. So like first like the alcohol, it turns into aldehyde because of the and all that, and then it vaporizes up and condenses down, and then it goes undergoes that process. And then
Yes. Yes. So it's like a bit stepwise with my weaker oxidizing agent, that it goes through the aldehyde to become the carboxylic acid. With my stronger oxidizing agent, it goes straight from the alcohol to the carboxylic acid.
So like if that is the case, like they don't, if like they use like potassium dichromate, they don't need to do the reflex, right?
We always, so when I say heat, I mean reflux. Because I can't, like I don't have a great way to heat something without using reflux. But the reason that I break apart distill and reflux is because I need to distill to capture the aldehyde, to prevent it from continuing to react.
But like I'm saying, like using potassium dichromate and it goes directly to carboxylic acid. Oh no, potassium manganate. Yeah, that's right.
Okay, I'm back with you then.
Yeah, so like it goes straight into carboxylic acid, so we don't use the reflex.
So it wouldn't really matter if you refluxed or distilled, the only product you're gonna get is the carboxylic acid and it's gonna stay on the left-hand side. You don't make the aldehyde, it doesn't survive.
So for the reflux, it's like that thing, and then on the top it's cold.
Yes.
Right? But for distill, when you capture it,
It's actually a closed system.
it's closed, but then it's
But what? Oh, but I have the condenser tube and the ice bucket.
And what is that condenser tubing back? What does that prevent?
So the condenser tube, it condenses the gas back into liquid because it's jacketed with cold water.
Oh,
So I'm just
your-
chilling
those
it.
things that you have open, you're putting.
Yes, I'm putting cold water in.
And that third arrow where it says heat, was that just the,
Heat?
yeah, that, what is that?
So I don't say reflux except for when I'm trying to make this, I can get the carboxylic acid or the aldehyde from a primary alcohol. There I have a choice, and so there I try to tell you how I'm heating it. But generally speaking, in organic chemistry, the word heat means reflux. I don't write reflux everywhere. There's not going to be test questions about reflux unless the question has something specifically to do with how do you get an aldehyde instead of a carboxylic acid or like that specific process. So Emma wants to know how you know when the reaction is finished. So because this is an oxidation process and you guys helped me figure out that chromium started in the +6 oxidation state, when the chromium is reduced, it's actually going to become chromium +3. When the manganese starts in a +7 oxidation state, when the manganese is reduced, it's actually going to end up in the manganese +2 state. Fun fact, this is yellow, this is green, this is purple, this is colorless. Karthik is like, do I have to memorize that? And the answer is frankly yes. So I'll do it again. This is a yellowy orange, this is green, this is purple, this is colorless.
You're right, great. So is there like a specific way that they change like the twos, or is it just random? So like it goes from 6 to 3 and then now it's 7 to 2. Why?
Because I have put a lot of acid in there to try to make the complete reduction occur. It's really hard to get back to the metal ore to make manganese or chromium metals. This is like a logical endpoint where it's stable. If you don't put enough acid in there, this one's pretty famous for making manganese 4. And that's some brown sludge. So if you talk to my girl Naomi, she didn't have enough acid in one of her reactions. She ended up with a brown endpoint. You're like, oh, you got to use that 85% orthophosphoric acid. It'll fix it all.
So it's just gonna end at 2.
So right, it's just a logical end. You can't really get it further using the kinds of chemicals we have present. So it is a logical endpoint. This is the change in the oxidation state of chromium or manganese. So the colors are orangey yellow, green, purple, and colorless. And this guy over here is brown and solid. Winkler girl, you actually make this on purpose. Winkler is quite related to all of manganese chemistry.
How'd you get the oxidation?
I magically have studied chapter 9 in your absence, Mohab. I thought we did it the last day of IB year 1. So traditionally the last thing I teach in IB year 1 is oxidation number. I don't know if we did. I don't know where we were last year. It was tough.
I doubt.
So in my head, I've done it. So it used to be that people wanted to take the chemistry SAT, which doesn't exist anymore, but remember when there were subject tests? And so that is one topic that I wanted people not to fail at. So I did a 1-day Uber lesson on chapter 9. So I still dream that I do it, but I don't remember if you did it, but you're accountable for it either way. Did you not do it in freshman chemistry?
Regular chemistry, and I'm preparing for every single specific test, other than that one topic.
There are a few other things that are missing, but we're going that way. Year 1 is gonna be AP Chem, we think, for the next year's juniors.
So what Randy just asked, it needs to be in an acidic condition.
Yeah.
Why does it need to be? And then
Have you balanced redox reactions before? Have you balanced redox reactions? Audrey's done everything. Like, she took this full class at her previous school. Like, have you ever played the game of, I have an iron tablet and I'm gonna react it with potassium permanganate to see how many milligrams of iron are in my tablet, and so the end point of the titration is gonna be colorless. It's gonna be purple to colorless, and I'm gonna make iron 2. Oh, bad, bad, bad. Good. And then you separate this into half reactions and you figure out that this is going from +2 to +3, so that's 1 electron. Is going from +7 to +2, so that's 5 electrons, so we need 5 of these, 5 of those. And then we count the oxygens and we say there are 4 oxygens here and there are none here, so I need to add some water. And then we say there are 8 hydrogens here and none there, and so we add some H pluses. And so that's the acid I need to add. If I don't have that acid, I can't do that reaction. You did not do this. Okay. Yes, we just do, so I like doing organic because you knowing if that's a ketone has just nothing at all to do with you knowing what a mole is, you knowing what thermochemistry is, right? Like, it's just, I think it's polite to start people on a bit of a clean slate. That's my motivation for doing 10 before 9. I think 9 is all of the stuff that you guys apparently have no memory of from last semester. Like, here we are again. So that's my motivation. I teach this when I teach Chem Honors, so I expect that people have a vague notion of it. Like, I don't expect that most of you can balance that equation without practicing, but the idea that we can count, we can bookkeep electrons, I feel it's like formal charge.
I didn't take Chem Honors.
That's the prerequisite for the class. The fact that you didn't take the prerequisite but have 100% of my permission to be here, like, you're killing it. You're amazing. No one in this room learned this in Chem Honors, so it's not like you did anything wrong.
I remember doing it, I just never failed.
Okay, like, so, like, we have no problem with this.
I have a question.
Yes.
The last, error thingy of the alcohol thing,
Yes.
the, K manganese, this thing, what, is that for a 1' alcohol?
Like, so a primary alcohol can only become a carboxylic acid if you use permanganate, because it's not, it's coarse.
Okay.
Like, it can't get that little aldehyde thing. So aldehydes are kind of hard to make, right? I think that's the point I want you to take away. Like, we have to do a trick to get that aldehyde. We have to use a special reactant, the more gentle one, and we have to set up the experiment fundamentally differently. But the questions are going to be like, how do you make an aldehyde, or what's the molecule based on the fact that you can oxidize it twice? Like, the questions are not, I have a practice question. Don't worry, it's coming. Good question. Tell me when it's over, and I'll decide what to do
Is the
next.
answer to that question carboxylic acid?
4 minutes.
What's the molecule? Oh no, it would be the K2CR2.
So if you can oxidize it twice, we know it was primary.
Primary, oh yeah.
What did you decide I have? Don't feel like you decided. Yeah, we'll do 11 after 10. Oh, you're trying to decide when class starts now?
Yeah, no,
11,
yeah.
10:55.
10:55, oh, I thought it was 11.
I think it's 10:55.
I think so.
You could do early today.
Oh, it's 12 in the morning. 11, 11:40. You have to be in class by 11. If your teacher's like.
Wednesday.
Yeah.
I have one 2-minute thing to tell you about.
Yeah, like if your teacher's for safety.
A homologous series is a word you'll see as a vocabulary term in 10.1. Homologous. I feel like y'all might know what homologs are, analogs, homologs, I don't know what the difference are. But the idea here is that it's a series of things that behave similarly. And the reason that they behave similarly is because they have the same functional group. But you add a CH2 group. Back correct my double quotes. I don't know why this is my disease today. I apologize. I'll go home and reread eat shoots and leaves so I don't use weird punctuation. We call that a methylene group in my culture. So CH4 is methane, CH3 is methyl, and CH2 is methylene. Methylene. We'll use that a lot in chapter 11 and not much today, but just because I wrote it down, I thought it was a good definition moment. All I wanted to do, because you told me I had about 2 minutes, was to say a homologous series is a series of molecules where I choose a functional group and then I just keep going along and adding CH2s. So an example of that would be if I start with methane, I'm going to go along and I'm going to add a singular CH2 group to it.
Is there a header?
No. The idea of this is that I'm going to have similar chemical properties. That's why my map that I erased is so good. Alcohols are going to behave in one way, alkanes are going to behave in one way, but I'm going to have slightly different physical properties because I'm going to make these chains longer and longer. Is that reasonable? So homologous series is just a series of molecules that have the same functional group where I make them longer and longer by adding CH2. Homologous series. Yeah. Thought it was a good 2 minutes. It was on my list. Yes.
I mean, the same general form.
Yes.
Yeah.
Absolutely. Same general formula, same functional group, same chemical properties, different physical properties, trending physical properties. Well done.